So here's where we are so far. We have these four equations and four unknowns, and we want to solve for these unknowns, which are the importance scores of the web pages. So let's look at our equations for a second. These four over here. We should note that the denominator in each of the terms is called the out degree of the node. So this 3 right here is the out degree of P4, because P4 gets divided by 3 since it has 3 outgoing links. In the same way, we can take another example, for instance, of P3's node, which gets P1 over 2, and this 2 is the out degree of node 1. At the same time, this 2 in the P2 equation is the out degree of node 2, and this 3 in the P4 equation, again, is the out degree of P4. So now that we understand mathematically how we build these importance scores, let's try to solve for them. So to make our lives a little simpler, we're going to first think about exactly what these importance scores are representing. These importance scores are really probabilities. And if you don't remember what a probability is really just a chance, or chance of an event. And so what we know about probabilities is that they always have to sum to 1 if we consider all of them. Basically, P1 is the probability that we're at node 1, P2, probability that we're at node 2, P3 at node 3, and P4 at node 4. So we have to be able to sum all of them to 1. Plus P4 has to be equal to 1. This is a really convenient equation to use, because doing this math out and solving these four equations can get kind of messy. So we'd rather be able to stick it into this equation and do some substitutions into here using some of the equations that we have. But we only want to use 3 out of the 4 equations because we have 4 equations if we're going to be using this last one over here. So which ones are we going to choose? Well, it turns out that it doesn't really matter which ones we choose. We're going to get the same answer no matter what. So how about we take the easiest ones, the ones with the least amount of terms? We can take P1, P2, and P4 equations. So there's really a wide variety of ways that you can go about solving this, but let's just try to take the least tedious route possible. We want to get everything in terms of one of these variables. Now the easiest one it looks like is actually to get everything in terms of P4, because we already have P1 in terms of P4 from the first equation. And once we have P1 in terms of P4, we can pretty easily get P2 in terms of P4. And then we can also get P3 in terms of P4, and we can solve out. So, again, we said we already have P1 in terms of P4, and we want to in the end result, we want to be plugging into this equation down here. So let's see if we can get P2 in terms of P4. Well, we know that P2 is equal to P1 over 2 plus P4 over 3. But we already know what P1 is, so we can solve in for P1 to be equal to P4 over 3. So we have P4 over 3 over 2 plus P4 over 3. And that is equal to, so P2 is equal to P4 over 6 plus P4 over 3, which is equal to P4 over 2. So P2 is equal to P4 divided by 2. That's one of our equations. So now we have P1 in terms of P4, P2 in terms of P4, and now we just need to get P3 in terms of P4. And so, how can we think about doing that? Well, we don't really want to plug into this equation for P3 directly because it has 3 terms. So let's try to use this equation for P4 and rearrange it. We know that P3 is equal to P4 minus 1/2 P2 from that equation. And that is equal to P4 minus, then if we substitute in for what we just saw for P2, minus P4 over 2 divided by 2, which is equal to P4 minus 1/4 P4, which equals 3/4 P4. So now, we can go on to the next page. If we compile our list of equations, as we said P1 is equal to P4 over 3, P2 is equal to P4 over 2, and P3 is equal to 3/4 P4. So this P1 plus P2 plus P3 plus P4 has to be equal to 1. So P4 over 3 plus P4 over 2 plus 3/4 P4 plus P4 has to be equal to 1. And if we solve this out, we have 1/3 plus 1/2, just factoring out the P4, plus 3/4 plus 1 times P4 is equal to 1. Now this sum, if we add these fractions together, turns out to be 31 over 12 times P4 has to be equal to 1. Therefore, we can conclude that P4 is roughly equal to 0.387. Now, the rest of it becomes pretty easy because we have P4, and now we can use this equation to get P1. So P1 is equal to 0.387 over 3, which is equal to roughly 0.129. Similarly, then, now that we know P1, we can get P2. P2 is equal to 0.129 over 2 plus P4 over 3, 387 over 3, which is just 0.258. And finally, P3 is equal to 3/4 P4, as we said, which is just 0.290. 290, 0.258, and we've got 0.129. And so, this is pretty interesting because now we have a vastly different picture than we had before when we just looked at the in degree. Specifically, we have P4, which is equal to 0.387, being now the most important node. And we have a clear-cut ranking, P3 being below P4. So we have 4, then we have 3 at 0.290, then we have P2 at 0.258, and then we have 1. So it goes 4, 3, 2, 1 is the ranking from most to least important. So what's the difference from before? Well, node 3 now is no longer the most important node. As remember before, node 3 had an in degree of 3. So why is it that it's no longer the most important node? It is now the second most important node. The reason is that node 3 spreads all of its importance score out to node 4. And it aggregates importance from half of both page 1 and 2, which are both less important nodes. And it only gets a third of P4's importance. So everyone that's pointing to P3 is really splitting a lot of ways. And these two are the less important nodes, and the more important node is only splitting a third of it to P3. But perhaps the most important point is that now node 4 is the most important. And as we saw in the previous figure, node 4 has one link from P3 and also one link from a very non-important link from P2. Well, that means that P3 is pushing all of its importance score directly to P4. And P4 is also getting more importance from another node as well. So P4 has to be greater than P3 because this is greater than 0. And this is just P3. So that pushes P4 to being the most important node. So the next question that we want to ask is, will these equations always work? We just came up with a way to compute an importance score of a node, where basically we're saying that a node, say node Y's importance score is going to be equal to all the nodes that come into it divided by their out degree. So P2, out degree of 2. And will this always work? And the answer is not quite. We have to make a few fixes to these equations in order to make sure that they will always work and they're always guaranteed to have a unique set of importance scores.